on the topic computational modeling of atomic clusters by Professor Anoop Ayyappan, Indian Institute of Technology, Kharagpur. Professor Anoop Ayyappan, the Associate Professor of IIT Kharagpur, he is from July 2010, working as the Associate Professor in IIT. He had his PhD in 2005 from the University of Hyderabad. The supervisor was Professor E.D. Jemis. He is a postdoctoral fellow. He is the he has instituted for physical and theoretical chemistry, University of Bonn, with Professor Frankie Nies within 2009 and 2010. He was a Max Planck Institute in Germany with Professor Walter Thiel. He has worked during 2006 and 2009. He is a member of the Chemical Research Society of India, that is CRSI. Again, he has worked in World Association of Theoretical and Computational Chemists. He has received the Max Planck Fellowship during 2006-2009. He is a member of the National Academy of Sciences, India. He has about 40 publications. His research interests are computational study of reaction mechanism, structure and bonding in novel molecules and clusters, developing methods to predict reaction and aggregation. Now, I welcome Professor Anoop Ayyappan for his presentation. Thank you.
Thanks a lot, Chairman. And also, I would like to thank the organizers for inviting me to this talk. Reggie Thomas is my junior, and so in MG University. So yeah, I thank all the organizers, Professor Pradeep.
He's beside me.
Including me. Yeah.
Reggie Thomas.
Yeah. Okay. Yeah. So you can see my slides. Oh, no, I think I have to share it.
Yeah.
You can start sharing.
Yeah. Okay, is it visible?
No, sir.
Only see the background.
Yeah.
Ah, okay, that is my slide.
Yes, yes. Okay, okay.
Okay, so let me try to move the slide. Yes, it's moving. Okay. Okay, so today I'll talk about my work on computational modeling of atomic clusters. Today we have also had some talks on nano materials, nano clusters, atomic clusters, etc. So what is atomic cluster? This is a Wikipedia definition. Atomic cluster is an ensemble of bound atoms or molecules, intermediate in size between single molecule and nanoparticle up to a few nanometers in size. So one of the most important or interesting thing that attracts me is the property of this material at a sufficiently small size evolves as a function of size from single atom to the bulk. And the problem with understanding these materials is that it is very, very difficult to experimentally characterize these small molecules, atomic clusters. It needs highly sophisticated techniques. Therefore, one of the alternatives is to use computational modeling of these atomic clusters and then do the theoretical analysis of their properties using computational methods. So that gives us a very good understanding that will help for future designing of the molecules and development of the field in general. So the such modeling requires, basically we have to search the entire chemical space to see what is the best geometry that is possible. So that usual technique is called global optimization. So I will talk something of all this. So what I will do first is how do we model these atomic clusters? And for that, we develop some methods that are some automated methods to do this modeling. I will explain about that. And then some study of the properties. So it's only some exemplary things are given, not that it's not a detailed application talk. It's more of that I want to show some of this modeling and how to do these things. And it is also, the talk is also designed partly for the students. So we will first talk about how do we model molecules for the computational studies. So this is a demo. I can say this. So take some of these softwares, which are modeling softwares. So this one is Avogadro. So I'm just showing a particular example where we try to model gold clusters. So we take the gold atom. So the second atom, adding a second atom is easy because there's only one parameter, distance. The moment you have the third atom, you will see that there are more possibilities. At least two possibilities, that the triangle and the linear. And there is all intermediate angles could be possible depending on the metal, the structure. So now it is 4. So the possibility is further increasing. So we can see 2 now, but there are also other possibilities, like you can have a triangle and one extending outwards. Can you think of another? Yes, I can think of further geometries. So something like a tetrahedron is a very familiar geometry. So that is also possible here. So we can also model that. So let's go just one step further. So 5 atoms. So how do we model that? So we can add this 5th atom to all of these molecules at various positions. Can be linear. Can add one more atom to this. And also can add one more atom to the edge of this tetrahedra, or at the side of the tetrahedra, say extended atom. One more at the edge. So these are all possibilities which we can draw manually. We can create these structures manually using any of these graphical visualizing programs. So as you see that these are extensive. We have to take all these structures, and this is a simple cleanup optimization, not a serious one. And then after we model all this, but then what we do is we try to do some calculations. That is optimizing the geometry, finding out the energy and other properties. So these are all has to be typically done. So we create this one molecule and then set up the calculation where, okay, so this saving the atom, optimizing, basically cleaning up application. Then we can choose any of the software and then set up certain parameters like what do you want to do, geometry optimization, which method you have to use, the DFT, and some parameters we can set, some advanced parameters, etc., which are typically the parameters of the job. So after that, we save the molecule, save the input file, and then run the job and analyze the properties. So I just give you a very short introduction of a one course material. Okay, so don't expect to know too much from this, but yeah, this is what we generally do, saving the molecule. So what separately we have to do for atomic clusters? We'll see. Okay, so now we will see how these molecules are represented. So we have just dragged and dropped and drew the molecule in the graphical visualizer. Okay, but computer, how does it know it? How is it represented in the computer or in for the calculation? So how can you represent a geometry? How can you represent certain points in space? We can use the well-known Cartesian coordinate where there is an origin, and then the points are kept as a distance from the x-axis, z-axis, and y-axis. Similarly, there is another type of representation called internal coordinates, where it is represented using the distances, angles, and dihedral angles, which is the angle between two planes containing 3 atoms. So this is another way of representation, these internal coordinates. This is somewhat easier for us to make it if you want to construct from so-called Z matrix, We'll show this here. So the Cartesian coordinates are easy for the computer. When you make it, it's very easy. But if you have to intuitively think about a point, okay, the origin is easy, that is 0, 0, 0. And anything on the x-axis, y-axis, z-axis, they are easy because then you have to only know the distance from the origin. But anything that is in between these axes is very difficult to intuitively think about that. We can use a lot of trigonometric calculations and make that. But there are other systems that is called Z matrix, where you represent the atom based in relation to the positions of the other atoms. So you can Z matrices like this can also represent the molecules. So then what we do, we have the molecule, its geometry and certain input parameters, and we calculate the energy, the first thing. So you might have heard about, about quantum mechanics and the Schrodinger equation, etc. And we can use some approximate methods based on these wave functions. They're like Hartree-Fock and post-Hartree-Fock methods. We can also use classical mechanics to roughly get an idea about the system. Or if the system is too large, then that becomes the only option. Molecular mechanics, that's very fast, but accuracy is limited. And then we have DFT, the density functional theory, which is very popularly used these days for real life system size, like few hundred atoms. There, the DFT becomes the choice of the method. So we can choose this method and calculate the energy. Okay, so these are our standard. So what is this energy means and what is this optimization means? So there is a term called potential energy surface, which is a surface containing the energy with respect to the coordinates of the system. So if you change the molecular shape a little bit, then the energy changes. And systematically, if you put these things in a surface, then we get this potential energy surface. So a simple example is a two-dimensional or one-dimensional potential energy surface. Suppose we take two atoms, for simplicity, hydrogen atoms, and keep it far away. Then when they don't interact, their interaction energy is 0. But when they come closer, they start to interact, and then the energy goes down and it reaches a minima. And when you push them together further, their repulsive interactions dominates, and then their potential energy becomes too high. So this is a typical potential energy surface for one-dimensional system. So one parameter, that is the distance between these two atoms. Okay, but there are real size systems are not diatomic molecules. We have more atoms, and then the potential energy surface is basically, so this is a 2D potential energy surface, 2D, and then the energy is on the third dimension. So these are more complex than the previous one, but so I will try to explain a few important points in the surface. So one is the lowest point in the neighborhood, that is called a minima. This is same like the minima of this mathematical function. So basically all this is a mathematical function of energy with respect to the coordinates. So the particular point that is lowest in the neighborhood, that is called a minima, and that is very important. And then there is another point called transition state. So this minima is typically the reactants or in the intermediate. This is the things that can be characterized, maybe very short-living species, but it is still possible to characterize. But the transition state is something that is between two minima. So if you go from a minima to another minima, the lowest energy path between these 2 points is called the minimum energy path, and the highest point in that path is called the transition state. This is a special point in this function, that is highest point in just one direction, whereas the lowest point in all other directions. Maxima in one direction, minima in all other directions. So that gives us the transition state. And now again, coming back to this 1D. So if you just take this coordinate, then we can simplify this potential energy surface into this 1D plot. So where there we have reactants or intermediates, or you have products, or again intermediates in a multi-step reaction. And then we have transition states. So what we can find out from this? We can find the barrier to go from one side to the other. We can find the reaction energy, whether it is an exothermic reaction or an endothermic reaction. All this information we can gather from these calculations. Then optimization. How do we find this minima? That process is called optimization. Optimization is a general term used in all domains, but in this particular case, it's the same thing. It's a minimization, finding the lowest energy point in a mathematical function. So how do we find this? There are several methods. So whatever we drew in this graphical visualizer or making Z matrix, they are actually a guess for the starting guess for the molecular geometry. Then there are certain procedures, algorithms, and computer applications where the algorithms are implemented. There is update this position step by step until you reach the minima. So it's, some of these methods, this is basically gradient descent going down in the direction of the gradient. So it starts from some point and then take few steps until it reaches the minima. So what are the methods? One of this popular method is called the Newton-Raphson method, where the update is done by finding the next point based on the second derivative of the function. The first derivative of the function and its its functional value, and the first derivative of the functional value will give us the next point. So this is faster than just following the gradient, and say like steepest descent going to the direction where the gradient is highest, or the conjugate gradient method where another factor is added where it takes it faster optimization. So using some of this procedure, we can do the minimization. So we have seen, I have tried to explain all the things that is done in a manual optimization, manual finding of the geometry. So why we need something more? Because these are this is a lot of work. So we have to sit and draw all these molecules and then go through all this process of modeling, optimization, and calculation of the properties. So then what is the option? We can use the automation. Automation in the sense basically to eliminate the tasks that are monotonous. So whatever can be eliminated. So basically the idea coming from famously from Ford Industries, where they have automated all these parts where the human is used to do the things. So those things that are that can be eliminated, the monotonous tasks are eliminated. But this is not new in chemistry. In computational chemistry, there are various areas where this thing is used to in various extents. So like virtual screening is a large number of molecules are screened and their properties, conformation and analysis. So exploration of reactions, docking. So a lot of areas are there. So what we are going to do, we are taking important points from all these methods and use it for our purpose of building the cluster or finding the cluster. As I said, I am interested in studying the properties as a function of size. So the best thing is to do is to grow the cluster from bottom to the top, bottoms up approach. So how do we do it? This is a simple flow chart kind of thing, how we do the things. So first take an atom, then add another atom to that, and then generate several possible orientations automatically and randomly. So we are not sitting and modeling things, computer is doing all these things, and optimize all these geometries and select unique geometries, and then add one more atom and then go on this cycle until you reach the desired size or when your resource is finished. So adding an atom, so keep the first atom in the origin. So how do we do this automatically? That is what I am trying to explain. So add an atom at the origin, and then add one more atom in the axis, and then you need to know only the distance between them, and then you can optimize them using whatever functional energy methods we have. we can, using that, we can optimize, and then we get the optimized geometry. Then this becomes your seed molecule, and then add another atom to this molecule. So we can add, where do we add it? We can add it in all these possible places around this. Okay, so that is where automatically created random procedure. So generating several orientations randomly. So what we do is we create a unit surface, and on the surface randomly generate these new points and add the new atom to that point, and then separate them in such a distance which is like sum of the van der Waals area between these two atoms, so that there is no close contact, and which is not also not so far away. So keep it in that particular distance. It's all done automatically, and then do the optimization. So how do we generate these structures? And we also need to have some efficiency, so that same structure is not generated again. By random generation, you may generate the same or similar structures again and again. So to avoid that, generate the structure atom, and when you add a next atom, we have to see whether we are adding to the same place. So that is something we can do to eliminate the duplicate structures. So this new atom is added in a completely different place, so it is acceptable. This is also acceptable. But if the new atom is very close to the previous atoms, then it is not acceptable. So we keep a list called taboo list, so that we don't generate the same structure and again and again. So this is called a taboo search algorithm. So after making all the structures, what is the next thing? Next thing will be to optimize all of them. So it is also done automatically. All the structures are optimized one after the other. And so when we optimize, say from all the structures, we got these three geometries. And we know that, so now we see that although we, the bottom two, although we started from two different geometries, it eventually ended up into same molecule, the similar structure. So if we keep both of them, that is a waste of resources. So we will have to select some unique geometries out of this. So that is done using, so as I said, so the third geometry is not required because they are same as the second geometry. So how it is done, we use some machine learning techniques and like to automatically select the structures. We cannot manually go through all these structures and see if they are similar and all. So we have to use some automated methods, like a mean shift algorithm or k-means that is coming from the machine learning libraries. So using all that, we select some unique geometries, and then we add another atom to this, all these automatically and randomly. And then after generating all these structures, we'll have to optimize again. So we'll see how it is optimized. So we get these geometries. So these three geometries we got. So select such minima. So these are called minima. This could be local minima, and the best minima among them is called global minima. So we can take all these geometries and then go further with the analysis. So this code is available free of cost. You could download from this GitHub page. And so this is used also used for the automatic exploration of the reactions. So now some examples. If I exceed the time, please give me a warning. Okay, so let me show some examples. So this is a gold cluster again. This is from the real calculation. Initially, I was showing just a demo. So this is the best geometry for the gold 3 from our studies. And this is the for the AU4, AU5, AU6, 7, 8. So that was the gold structures, and now this is a study of the palladium clusters. So relative energies are plotted of the isomers compared to the global minima geometry. So for a lower structure like 4 atoms, there are only 2 geometries. 5 also only have 2 geometries. And the number of possible geometries also increases when the system size increases. And you can also see some for a particular geometry where there is a very highly stable geometry. The number of geometries also reduces. The number of available local minima also reduces. So this is a relative energy plot, and this is called a second order energy, which gives us the, if a particular structure, how stable it is compared to its neighbors. So this might be important, like when you do a mass spectra analysis. So the most stable geometries among them will be available, will be coming out in the experiment. So so we can also analyze this second order energies. We can analyze the binding energy. This is the binding energy per atom. If you plot the binding energy, it would linearly go down and we don't get much information. But you can also calculate the binding energy per atom. That gives us. So we also wanted to test if you do different runs, how does it change? Because these are stochastic processes. So it takes random numbers. So 3 runs might give 3 different values. So they are more or less comparable. So then we also made binary clusters. So the homo-elemental clusters have been studied a lot, but binary clusters are not so much because they are more challenging. Usual methods to do this is to take a particular composition and then do a global optimization study and find them. So what we are doing is slowly building from the small one to the higher one. So that is a difference. So this is somewhat easier. And then we, so we did all this same kind of analysis for the binary clusters also. And this will also give us some idea about the mixing energy, where which combination is more stable. I'm not going into the detail. I have also forgotten the details of this particular study, but these are possible to be done. So this is another binary cluster. And if you compare the binary clusters of 2 very similar metal, you can still see that the geometries are different. So that is also when you compare the geometries of, okay, that I'm coming later. So this is a ternary clusters, 3 elements, 3 types of elements. And so these models are, these tools are ready now. Now what we need is huge resources to run the calculation and get some interesting results. So now we have our supercomputer in our campus, so we are exploring more into that. So this is just, I want to show that the global minima for different metals or different elements can be very different. So carbon goes linearly, and the smallest geometry where it becomes 3D is also different from different metals. You can see that palladium already has become a 3D geometry, whereas platinum and gold have planar geometries at this size. So we can grow like this, and you can see like, so the carbon becomes very interesting linear, and then it becomes ring. And at some point it becomes coranoline type, and then the fullerene, etc. But those are actually very challenging, and it will require a lot of calculation to reach the number 600. So we have not done that yet. So these are some platinum clusters. So this was our paper that is published in Frontiers in Chemistry, a global optimizers for nanoclusters. So yeah, some of the very interesting geometries are found, like AU20. So got the global minima for that, which was like proof of principle that our method can find the global minima for this. Okay, so the simple gold things, gold thiolate things are more real, more actually found in the literature. So we are studying that currently. Okay, so what we are doing? So we are doing building atomic clusters in a Aufbau manner, like bottoms up, and then we can find several minima and global minima. We can do it for homo-elemental or heteroelemental systems. So then when we published this, one of my friend from University of Hyderabad, I mean, we studied together in University of Hyderabad. He is in San Diego State University now. he said that he has a requirement to look for a global minima of a particular structure. So he's interested in planar tetra coordinate carbon and other hyper coordinate atoms, carbons or other elements. So this is interesting for him in the sense this is interesting for several chemists, because usually we know about the tetra coordinate carbon, tetra coordinate and tetrahedral carbon. That's what we know from all our textbooks. But planar tetra coordinate carbon is not common. So there was proposal for that starting from 1968. There were theoretical studies. Hoffman said how to stabilize these systems. Schleyer found computationally identified the real minima for the first time, but they were not global minima. And then there were also some experimental realizations for these structures. So there are several approaches that are being done to find such geometries. So it is always like an important topic. It is always kind of some interest is there. So what about instead of carbon, what about boron and nitrogen? So they are also being studied. So he had intuitively made this structure based on a previous structure where the beryllium was the metal. And yeah, CAl for beryllium. Since beryllium is toxic and it is not many people want to work with beryllium. So he thought, okay, why not we try with magnesium? And he had calculated this structure, but there is always a question that, is it the global minima? Did I miss the global minima? Is there any structure which is better than this? So one way to avoid is to try this global minima search. So we search the global minima for this using our procedure. And these are the minimas that we got. So this is the best one. So you can see the 0.0, that is the energy showing for the best one. And then the higher molecules, there is a tetrahedral species with the magnesium coordinated somewhere else. This is also magnesium coordinated for interacting with the electrostatics or whatever. So there are several geometries, we came across that, but interestingly, whatever we wanted, the planar tetra coordinate was the global minima. And also for we did for neutral and anionic systems. So these are long estimates for anionic systems. So there is a difference, but so this is planar tetra coordinate, magnesium is coordinated outside. Slightly different from the neutral system. So these are for the anionic systems. Then after publishing this, we also wanted to, so we also did standard molecular orbital analysis to see how they are, and we also did an ICS to look for the aromaticity in these systems. We did electron localization function to look at the interaction between the atoms. We also did Baird's charge analysis to look for the critical path and the critical points, bond path and the critical points to have better confirmation that they are actually bonded. So we get this bond path between these aluminiums and carbons. And so we also did some kind of ab initio dynamics to check the stability of the system at the room temperature. So this is stable, these structures are stable. These are the snapshots, which are very small to see, but basically the core is retained. Again, for the anionic system, the vibrations are more, the fluctuations are more, but again, the geometry is retained. So after we did this work, we wanted to extend this to another system where the boron is the center, planar tetra coordinate or hyper coordinate borons. So looking for that, we again did the same thing, the global optimization, and trying to find all the minima, including the global minima. So these are the geometries that we found for, so this is for anionic, I guess. So this is the geometry. We see that 4 bonds. And here we see that 5 structures. This bond is there or not, that is depending on the visualizer. So we will have to analyze properly to find whether there is a bond or not. So that kind of analysis is also done. So these are tetra coordination in boronic systems. And we also found systems where it is hyper coordinated. So we can see the bonds between them. So these are hyper coordinate boron systems. So they are interesting. So these are all what I want to show today. And what we are doing, we are also trying to, since you have these methods, and we also have interest in trying to find the atomic clusters of different elements. So we will use this method to look for different atomic clusters. And then with a friend of mine in NIT Durgapur, Dr. Subhash Kaushal, we have a NSM project where we will try to generate a database of all the hydrocarbon geometries of various combinations. This is in relation to the astrochemistry, looking for hydrocarbon molecules in the interstellar medium. And then we are also trying to model gold thiolates. This is, we need to modify our method to incorporate thiolate molecules automatically into the gold core systems. So that we hope is going to be a very interesting system. And now it is time to thank the funding agencies, IIT Kharagpur, SCRB, National Supercomputing Mission, and DST project, which gives funding to the department for some computational facility. And also I should thank my students. This is the left-hand side is all the previous students and the right-hand side is current students. It's not so updated because the newer students are not in the campus. These are more than 2 years old. So that's all from my side. Thank you once again for the listening and also giving me the chance to share my research. Thanks. Thank you.
Now it's open for discussion.
Anoop, very nice. Let me ask you one question to begin with.
Yeah.
Glad to see these cluster research that you are building up. Yeah, as you know, I work on noble metal clusters with thiolates. These days also with hydride and also unprotected clusters.
Yes.
Now, I was curious to see the difference. In gold 13, it is icosahedral. But palladium 13, you showed a different structure, and you mentioned that structures are different, etc. Now you go to gold 20, it is tetrahedral, as you have experimental structure is also tetrahedral in terms for protected clusters. I was curious to know why this difference in the 13 and between palladium and gold. In both in cases, the structural stability is known to be very important and not the electronic. The icosahedral structural stability is shown to be quite important. That is my first thing. The second thing is that the moment you have you put any alloys like palladium Au12 and or such systems wherein the structure is retained but properties are drastically different. You didn't talk about any properties, but that's another kind of systems. You briefly mentioned alloys, I saw. Thank you.
Yeah, so yeah, the answer is we are yet to analyze that. So the basic thing has to come from the bonding, basically the bonding orbitals, the interaction from the core between the core metals, like a icosahedral system with one gold atom inside and very symmetrically arranged different the other atoms around the central atom, whereas palladium is showing a different global minimum. So this has to come from the bonding, but we are yet to analyze that. So our initial focus was to make the tool first, and then we got the structures, and then we are going to analyze step by step. So that is actually my idea, that is there a periodic table of atomic clusters? So the different clusters, how do they behave when you go from one element to the other? So my short answer is I don't have any answer right now, but it's very interesting, and your input will be much more valuable to find the interesting systems to look for. Yeah, we also studied alloys. As currently we only have the what is it, exemplary systems to check our model with the literature reported systems. So that's what we have done with this type of alloys, nano alloys. So this is actually much more complicated, because in our approach, if you take one metal and add another atom, another element, that is easy, you can keep on adding. But when you have two elements, our approach will have to be multiplied with that many number of, it grows exponentially or even higher, because different way of putting different atoms together. Just to give a simple example, like if you are adding one carbon and four hydrogens, the order of adding is important, because if you add one carbon atom first and add hydrogen, you will definitely get to methane. But if you are adding, say, 4 hydrogen atoms and then adding a carbon atom, you may not get to methane, because hydrogens will have already gone to the H2H2 geometries and 2H2 dimer, and then adding another carbon atom may not break that bond and come to form a methane. So that is, we need to take care of all the possibilities so that we get all the structures. So the computational cost is too high. But we are into that. We have our supercomputer. Hopefully we'll have something. And we will be looking for important system to study. And I have also seen your computational study on the gold tablet systems. So I hope, I will talk to you later, and I hope you'll have some time to discuss.
Sure, thank you.
Thank you, Professor Pradeep, for involving in the discussion. Any more query, please? Okay, I think now all are prepared to go for the tea. So before which, I would like to present a memento to our Professor Anoop Ayyappan. Please accept this. This will reach your destination in due course. Thank you. Thank you.
Yeah, thank you once again.